Oh wait, there is.
Right.
Okay.
You found it?
Yeah.
It's just supposed to say record at the bottom, apparently.
You're recording it? Very cool. It's up. It's up.
Where's the Zoom phone? All right, give me a
Oh,
second.
it's up.
All right, give me 1 second.
Make sure to share your screen though.
Yeah, I should be sharing already. Back sharing? All right, can we all see the screen? Yes, hopefully.
Yeah.
Quinlan's the only person here, and Michael's just spectating. So I'm basically giving a private lesson to Quan over there. All right. So let's get started. We'll throw together a Vivado project, and then we'll go through some of the source files and look at the RTL fan out for it. So let's pop into, what is my, I think it's this one. Cool. And then we just purge this. All right. And then we can run our Vivado. So the script, we'll call it like demo and then set a top. All right, let's make us a little Vivado project that's just through some funky scripting. So if we go here and we look in like scripts, these are things you guys can set up yourselves. ChatGPT is really good at writing like basic scripts, for example. So like this Vivado project setup one is just this stuff here, taking a device name. I use the set device because it's the main card that I'm always using for my projects. You can like set that differently if you want to. It's the same as the steps in the wizard, just on the command line because I prefer the automated versions. And then that will just run this create project script, which gets all of that stuff from here, and then it'll just set some of the basic stuff. That'll make you your project. So now we have a project. If we go back file, we can pop into the Vivado project, and we can go Vivado demo.xbr, and it should open. Look at that. Look at that. Cool. So now we have a Vivado project open. Make some source files. Let's call this demo2.sv. All right, let's get started. So we'll name a file. There's a Florida. What is it? Sequential logic in SystemVerilog. All right. So now we'll give it a module name. This is like our entities and everything. I assume we learned this in lecture 1. Give it a parameter, our parameter set, the module name actually. Of our parameters, those are always important. I'll also give it our port defines. All right, so parameter int, we'll call width equals like 64, for example. If you want multiple parameters, you can just go like this with comma separated items. So like this is width 2, for example. You can pass reals, you can pass anything on these parameters. If you have custom defined structs beforehand, you can also set those parameters. I don't know why you ever would use custom structs for parameter items, but it's most of the time it's used for port items. And then we will end module really quickly. And let's give it some logic input. We use a logic. You covered wire and reg differences already, Antonio, or is that not needed?
Covered what?
Wire versus reg differences?
No.
All right, you guys can just use logic as the main type. Think about it as like your standard bit. Reg and wire have a little bit different on the synthesis, where reg will try to put it in a reg, or it gives it the ability to do that. Wires will try to just make it an internal wire net. We'll call this clock. We'll give it a reset one as well. We'll give it some outputs, like let's call this one reg C, for example, and then some inputs. Let's do input logic A and B like this, and then output like this. Oh, needs a type. Right, there we go. And again, because it's sequential logic, we need a clock and a reset preferably. So the big thing that Antonio went over last time is the always com blocks. These are wonderful. They're basically just a stem off of the standard always block, which looks like this, but then it has its sensitivity list, and sometimes you do a little star, and that'll sense everything in between. The problem is sometimes you don't have control over what's going to happen as a result of that. If you don't write your code exactly how it's supposed to be written, it might synthesize to registers, it might synthesize to combinational pieces. You don't know. With combinational, you can guarantee that it's going to try to turn it into like a combinational block before it ever tries to latch anything, and that's through your blocking, non-blocking assignment differences. So if we had like C, we called reg C equals A and B like this, then it's going to do like a logical and like an RTL and a block for something like that. That's our always com block, and then that can be done inside of this thing here. So we could also do reg C is equal to A and B, and that will map it as a combinational piece. But if you mix and match combinational and sequential items inside of one of these always blocks, it's difficult to discern what's going to happen. So instead, we use what's called an always FF, which is just going to basically try to always register the items. Can't fucking spell today. Always FF like this. Pulse edge, we'll get a sensitivity list. You can do something like pulse edge clock or pulse edge resets. In terms of naming schemes for this, you have a few different options. So we have pulse edge clock, we can do a comma pulse edge reset, or we can just make this synchronous like this. All of these work. Difference between asynchronous and synchronous resets. Am I going too fast, anyone?
Yes.
A little too fast?
You're typing really fucking fast.
Oh,
We're slow, we're slow.
okay. So
It was really cool. And then we hear all the clicks and we're like,
okay, so we have our standard always block, standard Verilog. It's kind of impossible to figure out what's going to happen if you start to get into really big modules and everything. You have an always com, which was covered in last lecture, which will try to put things in combinational logic every time, and you have your always FF, which will use like a sensitivity list of some sort and will try to register like in the outputs. That's similar to how our processes work in VHDL. VHDL, a process mimics this always like at block. It does multiple things. It can do combinational, it can do sequential logic. With Verilog, SystemVerilog specifically, we have these different types of always blocks that will try to do one thing so you can make sure you don't make errors. Again, if you're trying to register outputs and you try to do that in a normal always block, you might fuck it up and it'll try to make it combinational, or it'll just turn it into a bunch of random nets and everything. Does it make sense so far, everyone?
yeah.
Cool. So we're in an always FF. Again, this is our sensitivity list. It's the same as how this works. This star just says everything that gets read goes into the sensitivity list. For always FFs, I recommend against using the star because you might read something that you don't explicitly want to be like read. You might want a synchronous circuit. You don't want to read sensitivities on like A and B, for example. You should only want to read A and B. For example, if your serial wants to read A and B only on a clock cycle and you give it that star, it may try to read A and B on those changes instead of just only on a clock cycle. So it's the wonders about the explicit defines for this. And then again, you can give it an extra bit and you can tell it that it's sensitive to asynchronous resets. Make sense so far? So we're going to do a synchronous reset for this. They're the best, in my opinion, for most of the things, since your synchronous resets can guarantee that you can use BRAMs and some of the smaller register primitives inside of Avado. If you try asynchronous resets, they're a lot easier to work with, but they won't let you synthesize to a few of the primitives, such as BRAMs. The difference between those are LUTRAMs just use LUTs to store information. BRAMs use these little memory blocks, but those are strictly synchronous in most cases. And then you get into some of the bigger primitives like a URAM, which is just a really, really, really giant VRAM. So stick to synchronous resets for now for most of your things is what I recommend. All right. A LUT. Lookup tables are these things that store your logic, so it pre-computes the output of everything. For example, if you put A and B inside, your synthesis tool or your implementation step will pre-compute that A and B should be 1. So then you'll go to put information in, it'll map it into the LUT, and the LUT will give you the output of it pre-computed. They're just little, exactly. Yep, it's a little memory that's used as a truth table. All right, so always FF, we need to check with our rising edge on our reset items. The exact same thing that we do with processes of like if rising edge or if clock, that parameter piece. I can't remember what the English word is for it, but the little tick that you can do of like rising edge like this, that's another thing that would be done here. Instead, we just do like this. Check resets. All right. So this is what the standard thing looks like. We check a reset. It's synchronous. This will only be evaluated on a clock. So on a clock, we'll check the reset. This is our synchronous reset. We love those. If I instead had pulse edge reset right here, it would check this reset asynchronously instead. But we're doing a synchronous reset for this one. All right. So this would be our reset logic. If we had any regs of any sort, so reg C, for example, might map to 0 on reset. We want to make that 0. And then all of this stuff here is our next state precedence. Moves our registers to their next object. I assume you guys have taken DLog by the point that you're in this course. So when you have a state machine, you can do it in a 1-process system or a 2-process system. Your 2-process system will define a next state item, and you use that to write into the current one. So we'll cover that really quickly. Let's make a floating little logic bit call it reg C next, like this. and it's only one bit. If I wanted multiple bits of logic, I assume Antonio has already covered this. So we would go something like, you know, if I wanted to 8 bits, we'd go like that. But this one's only 1 bit. So that's all we need for now. Reg C, and we'll call that to reg C next. So this is the, well, I've always called the register process. All right, and then moving on to our next state logic for like a generic state machine of any sort. This is done generally with what type of always block? Anyone? Yeah, it's good. Your next state logic is a combinational result of your inputs and your current state. So we should use an always com block for it, right? All right. So the fun about the always com block, again, it's the same thing as the wonders of our process. So we want to set a default value. If we don't have default values defined for things, a lot of the times you will get resulting latches. So the default value we want to put in reg C, if we don't do anything else to it, so our next state, we want to give it maybe, you know, a 0 or something. Make sense so far? Cool. Normally people. So this is the difference between blocking and non-blocking assignments. Oh, you did?
I did not.
Oh, you didn't? Okay. So the difference between blocking and non-blocking assignments is whether or not something will wait for the next line to evaluate before it changes value. So what that means is if we do this, for example, there's this concept called a delta cycle in a process. It will go to the very end of all of the logic and take the last assigned item to some item, and it will use that instead. So for example, on these non-blocking assignments, what we call them, they're blocking, non-blocking. These are non-blocking assignments, so it will wait till the very end of the process, the very end of the always block, to assign it a value. So for example, if I instead give this, you know, 3 different values, let's say I give it arbitrarily 0, I give it arbitrarily 1, or I give it arbitrarily like its next value. At the very end of this always block, it's looked through everything. It's going to give it whatever is reg C next. It's going to see 0, it's going to see 1, then it's going to see next. Does that make sense so far for everyone? Cool. Combinational items are simply combinational mappings. It will write the 0 into the reg C next on the net list in the synth level. And then once you go to the 1, it will try to do that afterwards. So for example, if I had A equals C and B, right, or let's do C, A and B, right? And on a clock cycle, I had A equals 0 or A equals 0 and B equals 1. So let's say A equals 0, B equals 1. Naturally, when I'm evaluating that, this is going to be 0 because, you know, 0 and 1 is 0. But if I had something like this, A equals 1 right here, then it's going to use this bit. It's going to use this information before it, and it's going to use that to evaluate the following statement. So it's called a blocking assignment. It blocks, evaluates the thing, and uses that for the following points. It doesn't just stipulate all the way through and find the last assigned value. Make sense? Okay, cool. So that's the difference. Always com blocks, generally, like the rule of thumb is you're going to use this equal your non-blocking assignments, or your blocking assignments, sorry, inside of your always com, and you're going to use your blocking assignments, your non-blocking assignments, your little, you know, thing that looks like VHDL, always going to use those in the FF. You can mix them. I highly recommend against mixing them. That will oftentimes fuck everything up significantly. All right, cool. So we've set a default value and we're in our combinational pieces. Now let's do some bridging based off, or let's make some states. All right. So oftentimes in VHDL, we have this thing like type state, you know, bruh, and we'll give that some values possibly. So like state, you know, state 1, state 2. That's something we can do in VHDL. That's not exactly how it works in SystemVerilog. Instead, we use what's called a type def. And we can use an enum. It's a, you know, C object. If anyone here has programmed in C, we should know what those are. Let's see, and then we'll call this, for example, a state T. I always use this little T thing to indicate that's a new type, because sometimes people will just float state and then you don't know if that's a variable name or a type name, because we do have to worry about typing when we're writing things. VHDL, if the typing doesn't match up, it'll like explode. SystemVerilog will let you get away with some crazy things on typing without exploding, and then you have to go and sit there and debug in your waveform forever. Everyone keeping up so far? So we've gone through our different types of always blocks. We've gone through blocking, non-blocking assignments, and we've covered this small new thing to define states.
In what type of always block can you mix blocking and non-blocking?
I don't actually know.
Always block.
There you go. Oh, there, okay. I've never tried. I've been recommended against it at every point, and it makes the logic all messy for stuff like that. And if I have a one process system, I'm generally going to try and always FF instead for that. All right.
The good thing about common FF is that it'll throw an error if there's like something that shouldn't be there. Like if there's something that's being synthesized as a register in a conv block, then it'll be like,
Our president, everyone. Wonderful. Yes, and if you want to, you can also use like assigns. I see assigns were covered last lecture. Assigns can also do some of your combinational assignments for you. Those in theory can help overlap into your always FF blocks. I recommend slightly against mixing those. Most of the time, those are used just for field defines, and I'll cover that in a later date, or maybe towards the end of this. All right, so we're on our types. Now we need to give all. We can just give these arbitrary string names of any sort. I can go give a comma. That's possible. The reason it's not highlighting this is because normally it expects states to be all uppercase like this. So it doesn't matter. In its state, we might give it, compute state. Let's go like this. Compute state. And then let's go give it a done state. Notice here I don't have a comma at the very end of this one. It's not like Rust or Lua where you can just have commas through an entire iterator list and AutoSynth for you. This is all you need for it. All right, sound good so far? Yep, it's a custom type. The other thing in terms of encoding for the states, so your states get encoded to vectors by your synthesis tool. So we can define that explicitly here. You can map it into a logic bit. This will already be done for you by Vivado, by Quartus, by whatever you're using. It'll do it for you. You can just explicitly define it here. You can also these things called decorators. There's something like this, I believe. This will be one hot, and then these are decorators. This tells Vivado that you're trying to do something with the following logic. This isn't a synthesizable item. FSM encoding is simply a little message you're passing on to your compiler saying, treat this following stuff or the following expression as something or with some configuration option. So if we've covered FSM encoding types, anyone know different types of FSM encoding? All right, so FSMs, you encode with some bits, right? If I need to store 3 possible values, how many bits do I need to store 3 possible values? 3 bits. 2 bits, good. That's a binary encoding for it. So for example, if we have, state 1 might be, 0, 0. State 2 might be 0, 1. State 3 might be 1, 0. That is 2 bits. That is what's called a binary encoding. Luckily, those change 1 bit at a time. If we had a 4 state, that might be 1, 1. So you can store 4 states in a binary. It's compact, but the problem is, timing-wise, it sometimes messes up in terms of you have to check both bits if you want to check if you're in a state. So think your state machine mapping on your next state process, like this thing, your next state logic, right? It's combinationally based off of your state. If your state's encoded as 2 regs for 1 and 1, you have to combinationally check both of the bits, and that's technically slower than checking just one of the bits. Yeah, this is just an example. Well, let's add a 4th test state.
Okay.
You don't. All right. So this is our binary encoding. We'll call this here binary encoding. All right, and then let's cover one other one. I assume you guys haven't heard of this. It's called one-hot encoding. This is the standard for most FPGAs and their mapping systems. There's other encodings called Johnson encodings and ring encodings. I've never seen those used before, unless you have cyclical FSM. Most of it has funny branching logic. So we're gonna have one thing called one-hot encoding.
what's funny? He last spring covered FSM encoding.
There you go. I think he only ever talks about one hot and binary.
Talk about one hot for one day and put on the exam.
Yeah, I remember grading that. I was like,
Really annoying. I got that question wrong.
The key for one hot encoding is it's going to use one single FF out of the entire bit mask to tell if you're in that state. So if I have 4 states, how many FFs do I need then? We're doing one hot. Say it out loud. Say it out loud.
I don't understand what's hot.
4. You need 4. Yep. If I have 4 states, I need 1 FF per. So instead, we'll have a 4 wide bit mask. So state 1. So we would encode that like this. State 2 would be this. State 3 is this. Exactly that.
Also exactly what they wanted and how you will state it.
Yep, exactly that. So when we need to combinationally go and check which state we're in, we know explicitly on the encoding that like the bit position means we're in that state. So state 1 means I have a 1 in bit 1 or bit 0, however you want to call it. This one I have a 1 in bit 2, bit 3, and bit 4. So you only ever need to combinationally check one item. You don't have to check multiple. And if I need to tell if I'm in state 4, how many like checks do I need to do? Yep. I need to verify that like so many values are a certain thing, or yep, because I have 2 bits. I have to look through 2 bits. I have to look at, because 0, 0 is 2 bits, 0, 1 is only one of the bits, but I have to verify that the other bit isn't 1. Otherwise, then I would be in state 4. For this one, we know it's only ever one bit that's specifying what state you're in. So I can just check this one, I can check this one, I can check this one, and I can check this one. Make sense? It's only one register I need per. And that's how the one-hot encoding. It's better for timing because checks cost time. The binary encoding, again, you need multiple. The combinational logic will start to fan out a little bit if you have a lot of states. The one-hot encoding, you sacrifice the space for the speed. So we look at this one-hot encoding. Well, I need 4 whole registers versus only 2 registers for the binary. The binary is more dense, but I need more checks, more expensive time-wise. And the one-hot, I need more registers, but it's much faster. Make sense so far?
Yeah.
All right, cool. Stay with me now. All right, so going back up to the F's encoding and thing, this is telling Vivado that I want to encode this thing here, which is my state. I want to encode that one hot. It will do that by default. Vivado will always try to one hot encode by default unless you use some funny synthesis, like way, I think they're called, or different versions of synthesis. It'll always try to one hot encode things, which is why you don't technically need this. All right, now let's write out our state variables. So we need 2 states. We need our current state, and we need our next state. So that's how we use it. Same thing as we're writing C or anything, the state, and then the name and the other one. This syntax is the exact same as, where's it going away? Control R, I think. Current state, next state. The syntax is the exact same thing as doing something like this. So this is the same as doing this. You can do a comma when types are the same. Does it make sense so far? It's just a little trick. So we saw that way at the top here. I did input logic clock comma reset because clock is an input logic and reset is also an input logic. Same for A and B. They use both input logics. And then if I had multiple outputs, for example, I could do reg B. And then if I had multiple at the very end, I wouldn't add a comma because you can't have a comma before the parentheses. Otherwise, your tokenizer will explode itself. All right, so now we have our states. All right, now we need to look at our states. We need to branch on states. So what do we do if we want to, evaluate if something is true, but maybe in a longer succession of? It's also a thing in VHDL. If I want to check what state I am, what might I use? You have an answer, Quan? No? Yep, exactly. Yep, use case statement. So, yeah, this guy's a genius, man. So we'd use this.
Like what type of conditional block would you use?
In a combination of block.
Yep, here we go. So this is a case statement. Our next state logic is based on the current state, and it's based on the inputs. So we'll have to change some of the inputs. You generally don't change the sensitivity list on the case you're just about in the current state, and then you do some of the branching logic inside for the input changes. Make sense so far? Cool. Alrighty. So a few things about the case statement. It's just this, and then it evaluates this inside of this. You can do fun things like concatenations inside of it. So if I wanted to, for example, branch on A and B, you can write that as an expression inside of it, and it'll evaluate that, squash it together for you. It's wonderful. We have another thing like this. It'll also do this. It did B, and it'll treat this as a 2-bit vector. So then my individual case items might be 0, 1, and then it might evaluate like this. Another fun part of case. It might do that for you, even though they're both individually 1. Small trick. But the main thing we're doing now is case evaluation, so we don't need this. Current state. All right. So routing current state. One big thing, case statements that you always kind of need, I recommend heavily, is a default statement. You don't have a default statement. Sometimes it won't work in sim. It also makes sure you don't catch errors on trying to latch things in synthesis. So the way that scope keywords work in SystemVerilog is generally, you can write default, for example, like this is completely legal with a little colon, and you can say, current state is equal to, or sorry, this is mapping next state. Next state is equal to our compute state. This is perfectly legal. And if you have a one-liner for default, like that you only have one signal you need to assign for it, perfectly fine. That's what I would generally do. But if you have multiple things you need to assign in a default, if I had begin and I had some sort of control logic I needed at the top, like output logic, control 1, control 2. If I had control signals on a controller of some sort, I might, and these had to be assigned here. If I needed to do this in 2 lines like this, then that's multiple lines. You have to scope it with the begin and the end. That's the same for if-else statements, everything. As we saw up here, we have a begin, we have an end. Our blocks always have a begin and an end. That's just the default of it. So we'll axe these really quickly. All right, so we have our default state. Now, what do we want to do when we're in, let's say our init state? We want to move to the next state. How do we move to the next state? We need to first see that we're in the current state. So let's say init state. Give it a begin and end, and we need to define next state as our compute state, because that's the next state we want to move to. Let's move over to something like our compute state, like this, and next state might move to the done state. The hand up? No, I'm blind, don't worry. Done state. And then if we're in a done state, we might go from here to an end and undo here. Next state might go all the way back to our init state. Make sense so far? This is how we go through our cases. Again, same thing in VHDL. You normally do something like this, and then it does the exact same thing with the begins and the ends, I believe. So now what if we want to do some branching logic? What if I don't want to move to the next state and compute based on something else? Yep, exactly. So I'm in the init state. What if I have, let's say, a go signal? Give ourselves a go signal here. Plain above us. What? Oh, yeah, they are. If I'm in my init state and I don't have a go signal yet, do I want to branch into my compute state? Probably not. So let's do this. We can go if go, begin, end. And we don't need that because we already have our, we'll cover this. Begin, end. Yep. And that just maps out to like AND gates and stuff, for example. All right, so your next state, then we want to move to compute state. But let's think about what happens if I'm not on the go, like go's not true. So it's floating or it's 0, it's just not true. What do I want to do with the init state? Do I want to move to the next state? Probably not. So I need a default defined somehow. That's already happened up here. We have a default right here. But you can also explicitly define next state, which is going to be safer generally. I never do this because I don't really care about safety, but you can just call this your init state. So if you do this statement, this will cover all of the possible evaluations of Go. But if you just have this up here, if it's some big long branch, if it's some big long branching of, go 1, go 2, like some special combination of that, you'd have to define the else branch for every single one of those. If I had go 1, and if go 1 is true, and go 2 is not true, and go 3 is true, you would need the branch else for all of them. You'd have to define next state for all of them. Instead, at the very beginning, if you just have, next state defined as init state, it's going to use that as its default. So technically, we can get away with just axing that. Does that make sense to everyone? So, yep, okay, cool. All right, compute state. So let's say we have some done signal comes from that generally. We can branch on some internal register, for example. Let's do that. All right. So let's do logic. Let's call it accumulator, and let's give it 7 bits of width. Makes sense why we're calling it that? Yes? Yep. Just an accumulator. Okay, maybe not on that, but why? We're just going to find a little 8-bit vector called accumulator and give it a next value as well. Because again, we're working with sequential logic. So we need something to hold the next value. Yeah, like with the state, we have, the state and then the next state. Then for anything else that's registered, such as an accumulator, we need, or a register, we need a current state and a next state item. Make sense so far? So if I need to update the accumulator, so accumulator. Yes, if you're doing a 2-process system, you have to do that. for one process systems, you can get away with something else. I will show that off.
We did one process in each state. I just did it for the sake of time. Like, you only want one. It's a short.
Each person process really does like the things you're changing, and then the next person is where it moves to the font, and then you combination spot. So that if
This
one
really
process
quickly.
moves it, and the other process just
Forms.
swaps it.
2.
It's good for like just readability, and also the big thing is that in the one process, all of the outputs are registered, and in the two process, they are not. They get updated combination. But as it goes over it in detail, if you want to read it. There's one process that only changes the state, and the other process is combinational, changes everything.
Yep, this is the 2-process system. I highly recommend going with the 2-process system for everything. Antonio covered the 1-process system. 1-process system essentially is this always FF. You can do this entire thing in a single always FF block, but it gets very hairy and it's very painful to debug because you can't see the next state. If you have multiple possibilities from state A to go to, you could go to state B, C, or E from A. You can't see that, like what it's going to transition to when you do a 1-state process. That's why 2-state processes are always recommended. SIT also recommends that. There are versions with 3 processes. I'm a fan of those for much larger items. That maps your output logic instead of doing that on mealy assignments, which we will cover in a bit. All right, so now we want to branch our compute state item. So when we're in compute state, we need to compare against something to move to our done state. Let's say we want to see if a counter has reached a certain value. So we can use another if statement. We can look at accumulator. We can see, oh, if it's 10, then we should do something if we want to. We might go next state is now, our done state. Oof. Right. Next state moves to done state for our accumulators. But what if our accumulator is not equal to 10? What happens? What do we want to do? Yes, good. So next state is equal to compute state. Is there any way that we can do away with this else block on this if? Is there an answer over there? Yes, good. Where would I put that? Very good. Next state. I can put this in back to my compute state. Good. So if I did that, then it has a default, so it doesn't need any of this. So when the accumulator is 10, it will branch on that. Let's see if we have any errors in Vivado so far. It will look like it. Yep. I'm like 99.7, but I'm like z equals 3 that you can just do this. Some people love doing their little like what's called an implicit conversion piece like this. You can do that. I just don't care enough to. It does not matter. It will auto convert for you. A lot of people, like when they're, for example, when a lot of people are assigning zeros to SystemVerilog, a big thing people love doing is this little tick beforehand. That's basically auto sizing it for you. So if I, for example, wanted to assign reg C next into, like 674 on a decimal. Yeah, 67. If I want to give it 6767 on a decimal, it'll convert that automatically to the width of whatever I need versus an explicit width, which looks like this. Make sense? Same thing for zero. Zero is like, you always have at least a length 1 item. You don't have floating items. That's for some funky non-synthesizable verification stuff. Right? So you're always going to have at least 1 bit. 1 bit can be 0. You don't need this little ticker. Same thing if I want to assign it to 1.
So then when your accumulator was 1, 0, 10, how does it read it as 10 compared to 1, 0?
It just knows that this is a decimal because I've given it that way. And if it doesn't and it decides to fuck me afterwards,
You would just specify
Yep. You just do this little thing and you give it a D to just like say that it's decimal. It'll auto convert that decimal. So you give it this ticker that auto sizes for you, and then it sees this D. It thinks I see the D. That means all of the following numbers, I'm going to read it as a decimal. So when I do D10, that's reading this as a decimal 10, which binary encoded is 1010, something like. That's 1010. That's the same as doing, like B1010. Same as doing that. It'll auto convert for you. And that's down to the fun of like, I need to put $20, for example, with like an order engine of some sort, I want to put $20 on the bus. I don't want to encode that into binary. That's really painful. So I can just give it a decimal value. Same thing for some stuff you can do with floats. Generally, I'm doing decimal conversion. Same thing for hex. If I did this, then it would interpret 10 as 16 exactly. So we'll leave it like that. And then
when you assign logic like as a binary signal, like it is a binary value, right? Or
Yep.
logic is-
It'll convert to binary values for you. Bot will do that for you. Like,
when you assign it, like when you declare accumulator, it's logic, right? It's a type logic, it's not a type in.
nope. Yeah, exactly. Yes. It'll auto convert like any ints you try to write into it into logic. So for example, if, we'll cover this in a second here. If I already say accumulator equals like 20, it will auto convert that 20 into its binary format. And if you want to be slightly more explicit, you can do the D20. It'll auto convert the D20 into the variant of binary to like, 10010, or sorry, 10100 to 20. It'll auto convert that and fill the accumulator. Like, even though we know accumulator is a logic vector up here, it'll auto fill that in the binary encoding. Makes sense? One of the fun parts of SystemVerilog is you don't have to do all these, stood unsigned or conversion factors. You can just give it a value. It'll auto shove that thing in there. Sound good stuff?
Yeah, but what would be like, I guess, more readable or like better code?
More readable, I always think it depends on what you're doing. Like, again, if I'm working with money, I'm just going to use the decimal 20. If I'm working with a bit like a special bit mask, I'm going to give it a fine. I'm going to give that a local param instead. I'm going to name it something. So for example, like a bit mask, or what's more readable, we'll go like local param int, or go like this, local logic, 70. Let's call this bit mask 1 that we want to name it. Oof, I hate that. Redo, call out bitmask, call this bitmask 1, and we'll say this is equal to, 8 explicitly. In binary, we'll call it 1010, 10000. I think that's 8, 1, 2, 3, 4, 1, 2, 3, 4. Okay. And I would call that bitmask 1. If I was doing that and I wanted to assign maybe my accumulator to that, I would go, accumulator next. Since we're setting our next, we'd call that bitmask 1. That's more readable. That's way more readable. If I have an arbitrary bit mask or whatever for any configuration reasons or something, or it's a special mask for, if you're doing a loop over something and you're trying to find the least value of something that might result in a bit mask, you would use a variable name or like a local param name instead of using something like.
How can you just declare, like, how come, or what difference would it make when you declare as a logic accumulator compared to a local param?
A local param is something that Vivado can compare against. It's just declaring, it's a very roundabout way of declaring a constant, essentially. Does that make sense? Yep. Oh, what?
I'm thinking it sounds like.
Yeah, close enough. Yeah, it will just treat this as, it'll treat any occurrence of bitmask 1 as an 8-width bit vector of, 101000. Yep, that's exactly what it is. Nope. That's what, these things are for. All right, cool. So let's move into the accumulator piece. So again, we're working with our state machine here, so we only need to use next signals on assignment. We can check against current signals and stuff. So we're checking against current state. And accumulator here, we're checking against the current value of the accumulator. But accumulator next, we want to do something too. What might I want to do with accumulator, the accumulator? Any ideas? Something I can do with the accumulator? I can accumulate. Yeah, it's good. I can add 1 to it. So we might go accumulator next. Oh, plus. I'm like 90% sure you can get away with this syntax. Recommend.
Because that's inside to block.
Yep.
I was going to ask, does it have all access to all like the C bitwise operators?
Yes, it does.
Like, but does it have the
And, SOR, or, yeah, you have access to all
is
those.
it compound as well, or is it just like, or it has to be like single sign, like and equals, or equals?
Oh,
No,
I haven't
there's
tried
not.
this. I haven't tried this.
There's plus equals, times equals, stuff like that, but that
For bitwise operators.
that just means accumulator equals accumulators plus 1. But you have to know the difference between blocking and non-blocking operators. That's a blocking operator. That's not what you want to use in sequential logic. So if you were in an always flip-flop block, you should not use that, like the compounding.
Makes sense? Cool. And yeah, there are some, like, the symbols, you can get away with a lot of things in SystemVerilog. For example, these are these funny little range things that will, for example, I need to range through bytes at a time of a value. I think I used that in a feed parser somewhere for ranging through all the bytes. I can pop over that really quickly, actually, and show you guys. Let's see, and then we'll go feed parser. We pop here really quickly. So this is a loop for combinational pieces. We can look through this and everything. And this is going from 0 to 64 of a byte array. But if I want to, for example, where's the assignment piece for it? Here we are. If I need to write If I need to write these 64 bytes into a 500-bit vector, those are two different types. A byte vector is 64 bytes, and those are specifically byte types. But I have a vector that's 512 bits long, which is 64 times 8. I need to move this into there. So you use like a for loop or something, and that will just fan out to all your combinational logic, and you can use these things, so your little range operators and stuff like this plus colon. Make sense? You guys will not need that. It's probably way more advanced than you need. All right. Let's say our accumulator next is now equal to what? If I want to assign accumulator next to something, if I want to accumulate 1, how do I do that? To what? I can't add 1 to what? Yes, good. Accumulator plus 1.
He did it.
Look at that.
But you showed him. You showed him.
In theory, we should probably do this in an else piece. All right, let's do this in here really quickly. And then let's give it a default value for our next as well. Give this a 0. Or no, we're just going to say this is accumulator. So if we're not in the compute state, then it won't accumulate. All right, now we've moved to our done state, right? After our accumulators moved to 10. Do I want to maybe do an Amelia assignment for everything? We know what Amelia assignment is, right, everyone? We'll take a D-log. Yes, yes. All right. So if I wanted to say, I had a done signal of some sort, let's say logic done. I move this here. If I can say done equals 1 now. Make sense? That'll do Amelia assignment. A more assignment would need an extra process that would look at the current state. It wouldn't set next state. It would only map the outputs for that. I don't recommend touching more processes just yet for things. All right, now in our done state. What do we want to do in our done state? Do we want to perhaps debalance our done state so we don't go through the machine many times? Does anyone know how to do that? So let's say we're in our done state now, but we want to guarantee that our state machine is only going to run one time when go is asserted. Let's say go is asserted for a really long time. For example, 1 second button press. The state machine is going to run 5 million times. But is there any way we can guarantee that it's only going to run once while that button is pressed for that second? You got an answer, Quan? Let's hear it.
Can you go back up to the states?
Oh, the states? Yeah, sure. Okay, here we go.
You should know because you're micro.
Yeah, she should know. Oh, the microbeat? Send it. Oh, yeah, sorry. Well, we move it back to the init state.
You're almost there. Yes, almost there. So we need to branch. I'll give you a hint. We need to branch on some sort of item. We need to see if something is true. Do we know what we need to see is true?
Oh,
No.
No. I kind of straight from the
yeah. I had a sign code name for
Oh wait, Quinlan left. I don't have to perform anymore.
Okay.
Dude, I'm breaking into stress right now.
I'll give you guys. So you need to pull.
Yeah.
Exactly. Good. Very good. Yep. Exactly. So if I press the button down and go's going to be 1 across a jillion states, this will go to the very end, but it's still 1. And then I say, oh, if it's still down in that entire next run, then just stay in the done state. Then it's just going to stay there until the button is unpressed, and it has to go through all again. So one of our wonders, done state, if go. Alrighty. Let's take a peek at this. Let's throw up a cluster project as well while we're here. All right, wonderful.
I just asserted done.
Pop up a cluster project. Give it not this. Educators demo 2. There we go. All right, so now we're gonna check some Now we're going to do some functional simulation. So we've checked in Vivado, we'll call our linting to check that our syntax is correct and everything. Like this auto runs every single time. It'll check your syntax. If I, for example, make a bunch of garbled garbage here and we control save, it'll update automatically here. And it'll give you a syntax error file and say, oh, you have an error down here. If we look at messages, it'll give you an error, syntax error in here. It points right to it. What's up?
For like if though, can you do like if exclamation mark though or no?
Exactly. That's a way to shorten it. So we already know our next state's going to default to done state if nothing happens. Then you can technically take this entire thing and instead just do if not go in and, or you can even shorten it to this. Next state is equal to in state. You can do that. Sound good?
I remember you saying that there wasn't like an inverter operator in SystemVerilog. There wasn't like an inverter.
There's an inverter operator. The main thing is try to do this combinationally. Try not to do them in registered items specifically. Registered items meaning don't try to assign them in like reg FFs or always FFs. Try to do that on a wire with an always com block and then assign the wire values themselves to other things. When I say wire value, I mean next state. Understandable. All right, cool. So we have no syntax errors. Vivado's not telling us anything wrong. Let's look at functional. So we'll just compile. We can run a compile script of some sort where we can, compile. We can, it's a systematic compile. We can go here, we can go compile, we can compile all or whatever, it'll compile our stuff. I assume we know how to set up a model sim project already. Yes, we all know how to set that up. All right, so we just added this into our thing. Project, add to project, we can go find the file. Make sure we don't click copy to project directory, otherwise no changes will get updated. And these things are a separate thing I was working on. You can, to phase them out of the build, exclude them from the build, you right click on them, properties, and then you can do not compile, and then it will not compile them. But you can keep them there. You don't have to go keep re-adding them to the project. Make sense so far? Cool. So I'm just using this compile script. The compile script runs this thing. Equate that to me hitting compile all. All right, this is clear. So we've compiled, all of our stuff works on that end. Now we need to simulate. Anyone know how to simulate? No, we don't know how to simulate? We can use our start sim. Let's pop this way. Gator, model sim and Quest are basically the same thing. So let's go this way. Is this running on this one? Where is this? Oh, this is in the feed parser.
I'm not like you, the rest of you.
All right, let's pop into here. All right. So this is our Questa project. This is where we are. Like one of the fun things about Questa and Model Sim, Questa is just an extension of Model Sim, is that we have full scripting access and everything. So I can sit here and plug in like a Linux command or standard Linux commands. It's called TCL commands that let you see where you are. So I'm in this folder, which means I can run all of these scripts. All the scripts I have, we can see them here as well. So if we go into our sim script, for example, it's going to do this operation. If I were to plug this operation in here, the opt-args equals plus ACC work dot demo2.sv, then it would try to simulate that. The problem is that's not a sim file, so we're going to quit that really quickly. All right, so we'll call this instead. Oh, I do need a test file in that regard. Let me grab a template for the test bench really quickly.
Free license, yes, but it has some functionality to the screen, but you can get access to the server that has full license.
You have a full license as well on the ECE server.
Yeah, that's what I was talking about. How do we get that? Well, I can say.
Just SSH in.
I got
All right, cool. Let's go fgator. I'm very close to typing a cursed word. All right, paste in one of my files here with a custom bash. This is my template for test benching and everything. SystemVerilog. That's a separate day to cover the templating, but we're just going to test this really quickly. So we called this what, demo 2, I think. It's demo 2, so we'll just call this demo TV. Call this, and we'll instantiate this like this, demo 2. And then we'll give it some values. So clock dot reset, dot go, dot done, and I did. I think it's-
I think fucking bro.
The fun part about that is Vivado will take them out. It'll do what's called a hierarchy flattening and just say, go away, we don't need you for anything. Unless they are directly read in logic. Like if I use A and B explicitly for something, then it will keep them there. Or you can also explicitly tell Vivado, keep this here. And it'll say like, oh, you're retarded, but I will keep it there. So this is what we call, I think it's this. This is the Verilog style for assigning to internals. .clock, .reset, .go, .done. Technically, you can feed in signals with just commas. Like in our standard C functions, I could do clock, I could do reset to our internal signals. These are our internal signals like T-ins, T-outs, T-resets, and everything. I just prefetch it that way. You could do, T-clock 1 and assume that the ordering is absolute for the module. Never ever do that. If you change the ordering for this module, so if I change anything about the ordering in this here, for example, I insert a new output logic bra right here, then some ordered system I have here would have to be changed to T bra or whatever my internal signal mapping it to is. All right, we will proceed with this a tad faster since you guys are not here for test benching. You guys are here for sequential. All right, let's give it an internal ghost signal. Fun or word. All right, let's give it T-go, T-done.
Give us a raise, man.
Then let's add this really quickly to our project. Existing file. Let's give it, why did I paste this into the timing speed parser here? FPG gators, templates. There we go. There we go. There you go, files. Wonderful. All right, now let's go ahead and simulate. And we'll pop over here. Vim sim script, and we're going to call it, what's this, work dot demo to TB. And then we do this, do our sim script. There we go. Office in our sim. All right, now we have all our internal signals and stuff. We need to start adding the internal signals. We can just call a command like this, recursively adds all the signals. It's the same thing as going into your view, your objects. You can look in the objects and you can add all these manually, or you can do, our globs. This, we can add all of them manually. That's why I always delete these things on the sides. I have more screen space, and then you can expand this out, and you have all of the internal signals accessed as well, because it's just recursively. So for example, I don't need clock 2, clock 3 are not useful for me. The enable is not useful for me. Our outs aren't useful. Nor is our example functions or any of that stuff. Don't need that. That might be for a verification thing later. Controls are also not needed for this. Okay, let's give this another clear because I'm slightly OCD. And now we need to do a run script. We need to, when we simulate, you can go run all, or you can just do like a run dash all. I have it written in a small script. We just run.do. And that's what proceeded. Makes sense so far? Okay. Let's do. Not working correctly though.
I'm so surprised because I do this. That is because I know you guys it's fun.
Current state moves to the next state.
You don't make mistakes, bro. It's industry.
Yep, current state should happen.
No, we are.
All right, so now we need to resim because I didn't set my current state's default value on reset. A big thing with encoding our sequential logic, our state machines ever, we need a default state. If you don't tell your thing there's a default state, it's going to explode. But when you're setting a default state, you don't set that when you're setting the variable exist. For example, it's called our variable initialization. We say we have a custom state, current state, next state. You don't go for example, let's uncomment this. I don't go and do this. That is not something you can do in you can do it in synthesizable logic. You should never do it because it's going to give you a mux is what it's going to do, and that's not what we want. Instead, you have to use a reset state for that. That's why resets are so important, because you start in reset state by default for any digital circuit. Make sense? Reset's purpose is to get you to a point you know. So when reset's high at the very beginning, I know now that the default value in reg C is 0, I know accumulator is 0, and I know current state's in init state. So now we need to resim. So I have a script that also does that. We'll just do this. Cool. And then it needs to move the states over. I didn't move the states over either. Current state needs to move to, state next. Next state. There we go. Compile. Look at the bra. All right, there we go. Oop. Current state, next state. It is still cooked. I'm no better than them. Accumulator. Oh, go is not asserted. That's why. So go is never asserted. Let's just assert go really quickly. So let's give it 15 nanoseconds to do nothing, and then give it tgo equals 1, and then give it 100 nanoseconds. All right. Like this again. There we go. Beautiful. So as we can see here, we're starting in the init state. Again, we give it 50 nanoseconds. It's 5 clock cycles worth of time to do nothing, and it doesn't have go, so the machine's not going to start, right? And then we hit go after those 50 nanoseconds, and it's in the compute. And the accumulator, as we can see, is going to start counting up. The big thing here, debuggability-wise, you can see accumulator. You can see what the next value of the accumulator is going to be, which is much easier to debug. If you have a one process system, you wouldn't have access to this accumulator next signal. It'd just be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you had any jumps, for example, of like 1 to 5, you wouldn't be able to see that the next is supposed to go to 5. Like, for example, if I wanted to go from 1 and it could branch from 1 to 5 or 1 to like 20 million, you can't see what the next thing is. It's just going to go to it. It's much harder to debug if you don't know what the next thing set to be is. Make sense so far? We all got thumbs up. All right. So the big thing we define this as, it's going to look for accumulator equals to 10. So I need to give it a few more clock cycles. Let's do that. Let's give it, 200. How much time do I have, Antonio? All right. Hell yeah. All right. So we have an init state, compute state. Once we get to 10, it's going to check against that right here. And then the next state is going to move into the done state, exactly as here. And it's going to stay in the done state for all the next clock cycles. Do we know why it's going to stay in the done state? Yes, good. Yep. Go is still asserted. So now I have to unassert go. Assert go after, 200, that's 270 cycles in total. So unassert go and then give it another, 100 cycles to run. And that's resim. There we go. So now after the done and after that time, we can see go right here. It is deasserted back down to init. Now we're just going to float in init because we don't have our go asserted. So that's how a state machine is going to encode. That's how we do that with a combination of our FF and our always com blocks. Tony showed how to do the next state logic with, like an always com. And then if I need to advance the registers over, I'm going to use this always FF. All right. And one last thing I do want to cover is the one process model for this stuff, which I think is a highlighting point of always FF. So we'll go ahead and do that really quickly. Comment all this out. All right. We'll copy this over. Let's go like this, yank that, and then 30 jump, 10 down. All right, let's do this.
Yeah, you can do anything.
All right, so now let's do the one process model. We can do this entire thing in only one process, and I'll show you why we want to use 2 processes instead of 1 process by demonstrating how this works. So let's go through our states again really quickly. So in reset, we want to set our states. We're only going to be working with current state in this one. We'll set this into init. It's all fine and dandy, right? We'll set done is equal to 0, and we'll set goes an input, so you can't do anything. Done is our output. All right. Now, what did we need to do to branch on state? Like, if I want to make decisions based on the state, what do I need to use? Yes, exactly. Case. So we can do case on current state. Begin. Oh, not that. And then end case. And we define a default. Default's always useful. VU, like this. All right. Do I have a default state I want to use? Anyone? Huh? We just say init state. We can default back to the init, or we can default. Yep, same one. We'll just default to current. We always want to default to current state. Let me make sure these are assigned correctly. These should be the blocking or the non-blocking. Doing a little oof there. It's going to try to register these as well, which we'll see on the RTL mapping in a second. So now let's. It does. I didn't show it. I'll show it in comparison in a second against the 2 of them, and then that'll be the end of the presentation because I'll start to bore you guys. Questa does not. It actually can. It's really shitty, and you should never use it. It's called a data flow diagram. Don't use those on Questa. They're poo-poo because the RTL viewer inside of this is much stronger. Yep. I can show you. I'll show it to you guys after the one process model. So if I need to look through my states, let's say we're in init state 1. What do I need to do in init state 1? What do we need to do in init state? Exactly. If go, the current state is going to go into compute state. Good job, Michael, my goat.
Social media like.
Compute state. All right. So in our compute state, what did we want to do in our compute state again? What did we do last time? Exactly. If accumulator is equal to 10, so let's do that little extra defined piece. If accumulator is 10, then our current state needs to move into the done state. And what else? Yeah, we're going to say done is 1, and then yes, we will do that. Else, yep, we have a done little done signal that points out to the thing. Otherwise, this is in compute state, and we need to say accumulator. And the fun difference here, that should be an equals and a plus. What would I write on the other side if I want to like accumulate? What's going on the other side of this non-walking assignment? Michael. Yeah, yes. Add 1 to what? Like, just tell me what I should write here. Very good, yes. So we can do our traditional like programming, you know, the variable equals variable plus 1. We can do that here. All right, very good. That's all accumulate. And if I'm in the done state, what's our behavior? Good, exactly. So we can just do, huh? Yep, you can show not go. You can check go and then do that fun branching and stuff. Or we can do if go, then this will move to what has this current state. It's going to init state. There we go. All right, and that should synth. What's up? Mm-hmm. Yes. Yep. It'll be registered. I think this also latches done, if I'm not mistaken. It'll latch one. We'll see the warning in a second. We'll see the warning in a second. Latching. Huh? Yeah, but it's gonna latch 1, right? Because it doesn't have another.
If it's in always FF, since it's registered, it's not gonna launch. It's gonna be registered.
Interesting.
Unless you've never defined it. That should be. I mean, define it as 0 somehow. Reset probably.
Yeah. Indeed. Otherwise, yeah, it would make a mux. Antonio is correct. Otherwise, it would make a mux. All right, so now that compiles. All right, let's do a resim. Very cool. There we go. Cool. All right, so under the same timing conditions, again, we have, you know, our reset asserted. So we're in the init state, and then we wait to assert go. We assert go. And now it's in the compute state, and it's going to start counting up all the way to 10, and it'll stay in its done state until the go's deasserted. We go here, goes deasserted. Now we're back in the init state. Now the key thing you notice here, we have no value for accumulator next. I can't see what the next value of this is going to be. And if I wanted to branch again, if I wanted to jump around from 1 to 9 to 7 to 6, I can't see what the next thing it's going to go to. It might jump to 2. I don't want it to jump to 2, and can't see the signals that lead it to that. So this is the difference between a 1-process and a 2-process system. We will stare at the RTL as well right now. So we go to RTL analysis, open the schematic. This always takes fucking forever, but whatever. All right, cool. It's going to fan out way more than it should, but this is exactly what it's doing. This is mainly for all of the default values. I'm pretty sure this does latch. Regsync, RTL mux. This is the state regs. Yep, exactly. So this is what you get. You get a bunch of ROMs. ROMs are kind of a funny synthesis on small stuff. It'll use that as basically a silly little LUT for larger constants. This is what it synthesizes to. It's just a bunch of muxes, regs, and everything, and we can run synthesis really quickly while we wait. We'll go. I can't change anything in synthesis, can I? We'll stare at this really quickly. The accumulator next. If let's do quit dash sim, right? Do sim. And then we pop open the view on the objects again. That doesn't recursively. Add wave dash r. This. Pop here. Go away. Go away. Go away. widen this, and the accumulator next. Accumulator next would not be there by default if you're adding in, and then you do our little run and everything. You wouldn't have the next, and you just can't see what's inside of the machine. You can see all of your other things. You can't see what the next value is going to be, and that's the big difference between the two. Now, so this is complete. Let's open the synthesized design. All right, it's the wonderfuls of the synthesis, and then I think I have to run implementation. Actually, yep, there we go. This is what all of our LUTs and stuff look like. It doesn't name them. Sometimes Vivato's just pissy about it. Let's see, was Leaf Cell a crash Vivato? No, I didn't. Not yet. So you have your clock controllers. No, these are clock buffers. Sorry, don't worry about those. That's more advanced than you guys need to worry about. Then we have things like this is a register, for example, a register primitive. We have things like our LUTs and stuff, which are somewhere around here. More accumulators. FTREs. Oh, here we go. Here's a LUT. This is one of our LUTs. We can identify here, and it says the primitive is a LUT3. So it's going to take 3 inputs, and then it's going to map out the value. All right. Now let's look at one other thing, being the two-process model of this when it's synthesized into RTL. So let's like this, and then like here, 30 jump up, like here. Whee. All right, let's do a really quick functional comparison. Oh, there we go. What's happened here? 71. All right, 2 more here still. 124 and 128. Control redo to AGG. That should have just fine. Wonderful. All right, and then we'll give Vivato a second to elaborate over it, and we'll open up the schematic. Give it a reload on the elaboration. Huh? Oh, I'm on Linux. So Vivato is a Linux native application. Like all of these tools are designed on Linux because that's what engineers use, or the machines they're using are just like dedicated servers for this stuff. Vivato runs way, way, way faster on Linux. For example, if I'm going into that implementation run, that might take me for a really big project. Like, there's some of the stuff I've done, like there's a 25-minute implementation process. That might take an hour on a Windows machine because the ability to multi-thread on Linux is much, much easier compared to the other stuff. And as we can see here, it's basically the exact same thing we saw with the one process model, slightly cleaner with some ROMs. This is our little ad. I don't know why it's not giving us the symbols on them. That's just a quirk of Vivato sometimes, but that's how it works. So yeah, that's our next state logic. Do we have any questions about anything I showed you guys? What's up?
So like, some extra experience level, what is just like a two-process model? Because that's what I do.
The one process model is fine if you really have a fine-tuned control of how the stuff works. I would use the two-process model for basically everything else because next states are much easier to debug with. It's very difficult to debug on one process. There's also our 3-process models. I use those explicitly for really large maps. So for example, a CPU, you have a controller and a data path. A controller might have a lot of outputs and stuff, and that's based off the state. The outputs are based off the state. You don't want to do the output assignment and the next state logic in the same process. It might get really messy. So use a 3-process for that. That's only for really large things. You take digital design next semester for the MIPS. That's something I recommend using it for. Otherwise, 3-process logic is generally, it's not frowned upon or work perfectly fine. It's just more stuff to type. Make sense? So like here in the 2-process model, so for always on next state, we assign outputs like done. We also update our state stuff. In a 3-process model, you would simply change the states. And then the like differences on the done and all of these other things would be done in their own process. Make sense? Like control signals might be an output of an FSM. That would be its whole mass of stuff. The next state logic might be super complicated. The control signal might be super complicated. So we can separate them in 2 separate processes. Make sense? 2-process logic, that's all you need for now. Cool. Any other questions about any of the quirks of Auto?
You also like split up like the thought process if you want, to like different groups. Like say you're working on like really popular examples, like you're working on like an ACTI interface, like how you if you looked at like sys memory and stuff, you see, you'll take multiple processes for different types
Yep.
of specific things. That can all boil down to just like two processes potentially, but you can split it up.
Yeah, you can divide a controller. So if a control logic is really, really dense, like decoding an instruction and branching and all of that, you can break that down into a bunch of controllers. For example, I know one of Boeing's instruction sets for one of their military ISAs uses like 6 controllers to break down its entire 700 states of control logic and everything. You can break them down to make them much easier to use. And one of the fun things with always com blocks is as long as you're not interflicting on your signal usage, you can make multiple always com blocks. So again, for example, on that feed parser I showed, this always com block is just for mapping that input and output stuff. But I've got another always com block down here, which is just like doing my main logic. You have multiple always com blocks. It's basically just like multiple processes. Again, as long as the things they're assigning don't overlap when they're assigning to them, you can read from multiple things. As long as they're not overlapping on assignments, you can do that perfectly fine. Make sense? Cool. Anything else? Tooling questions? Anyone?
I just saw give me your Vim profile.
I think it's on my GitHub. Maybe I haven't updated in a while, but
Also, you need every single line of code you wrote.
yeah, I'll upload those.
No, well, like, you do like a GitHub thing if you want. That's what you did.
I'll push these to a GitHub repo of some sort.
Oh, yeah, you did.
Alright.
But yeah, that's about what? No, it's just Ubuntu. Ubuntu, standard Ubuntu. But yeah, in terms of all the sim stuff, what? Was there any? I don't think any, I think Quinlan was there for a second and then he disappeared. All right, say bye to John. Yeah, the Questa things again. I'll push all my special scripts and stuff for all the simulation and whatnot. Otherwise, I'll say goodbye, everyone. So let's go ahead and do a quick dash.
That's so hot.